Again, this is construction. Let's see. We know that every rational number is positive, negative, or zero. We know that. We now want to say the same thing for the reals. Each real number should be positive, negative, or zero. Since a real number is just a formal limit of rational say, it is tempting to make the following definition. A real number x, formal limit tends to infinity, 0 is positive if and only all the n are positive. I mean, that's how we tempted to say. And negative if all the n are negative. And 0 if all the n are 0. However, one soon realizes some problems with this definition. For instance, the sequence a and n going 1 to infinity defined by a n equals 10 to the minus n, that is 0.1 blah blah blah, consists entirely of positive numbers, but the sequence is equivalent to the zero sequence. I mean, that is very easy to prove because 10 to the minus n minus 0 is equal to 10 to the minus n. This is less than any epsilon. After given any epsilon, you can find that. I mean, it's very easy to prove. Thus, even this is very important for you. Here we are saying that is 0, not because of we are thinking that it is going to 0. Because all the numbers are, terms are rational, we are looking at the definition. Given any epsilon, there is an integer capital N. After that capital N, for any simple n greater than capital N, 10 to the minus n is less than epsilon. That is why it is a different story that we know 1 over 10 to the n, limit of 1 over 10 to the n as n tends to infinity is 0. We know that. I mean, we are playing around the bush in a sense. Thus, even though all the rationals were positive, the real formal limit of the rational was 0 rather than positive. Can you see here when he says formal limit? Actually, we haven't taken the limit. What we said was that over there sequence and the 0 sequence, they are equivalent. You need to be careful. Another example he is writing that the sequence is hybrid of positive and negative numbers, but again the formal limit is 0. The trick, as with the reciprocals in the previous section is to limit one's attention to sequences which are bounded away from 0. That's how we can escape this problem. That's how when we say x is not equal to 0, then x was a formal limit of a sequence of rational numbers, non-zero rational numbers, which is bounded away from 0. That's what I wrote, and before the t. Let a and n going 1 to be a sequence of rationals. We say that the sequence is positively bounded away from 0. Positively bounded away. Now, so far we discussed about bounded away from 0, now positively. If and only if we have a positive number c greater than 0, I suppose maybe, he has positive rational c greater than 0, such that a greater than or equal to c for all n. In particular, the sequence is entirely positive. Every number is positive. The sequence is negative, bounded away from 0 if and only we have a negative rational minus c less than 0, such that a less than or equal to minus c for all n greater than or equal to 1. Like that, what is entirely it is negative numbers. Here is an example 5.4.2. The sequence over 1.1, 1.0, 1, etc. is positively bounded away from 0. All terms are greater than or equal to 1. The sequence minus 0.11, minus 1.1, minus 1.01, etc. is negatively bounded away from 0. The sequence 1, minus 1, 1, minus 1 is bounded away from 0, but is neither positively bounded away from 0, no. No, negatively bounded away from 0. That's clear, no? It is clear that any positive sequence which is positively or negatively bounded away from is bounded away 0. That is clear, no? Also a sequence cannot be both positively bounded away from 0 and negatively bounded away from 0 at the same time. That is also clear. Because it cannot be. No number can be both positive and negative. Definition. A real number x is said to be positive if and not only. Now he is defining a real number x is positive. If and only it can be written as x equals formal limit n tends to infinity an for some Cauchy sequence an, which is positively bounded away from 0. X is said to be negative if and only it can be written as formal limit of an for some sequence an which is negatively bounded away from 0. So that is his definition of a positive number, positive real number and negative real number as well. Let's see here. Basic properties. This is an exercise. See whether I should do it. For every real number x, exactly one of the following three statements is true. This is a trichotomy, no? You know the word. X is 0, x is positive, x is negative. A real number x is negative if and only if minus x is positive. If x and y are positive, then so are x plus y and xy. I guess you can prove it, no? I don't think it will be anything. Anyway, then according to you, next week, Friday, we are not going to lecture, we are going to discuss about whole 3 hours about the problems. Alright. But before that, this homework should, now his solution is correct, but the way written is lousy. So he should be instructed to know how to write because you guys know only A-level know how to write solutions to A-level problems. That is again not logical the way you write, no? Because even though mathematics is a language, if you look at the A-level answer sheet, no statements, only simplifications. Not logical, yeah. Anyway, note that if q is a positive rational number, then the Cauchy sequence q is positively bounded away from 0. And hence formal limit n tends to infinity q is equal to q is a positive real number. That is clear. Thus the notion of positivity for rationals is consistent with that for reals. Similarly, the notion of negativity for rationals is consistent with that for reals. That's good, otherwise we are not doing this now. Once we have defined positive and negative numbers, we can define absolute value and order. Absolute value, let x be a real number, we define the absolute value, we write these 2 vertical lines and in between x of x2 equal to f x is positive, negative x when x is negative, 0 when x is 0, that you know. Ordering of the reals. See, the reason I am saying is now you are thinking of this, how to prove this, you spending so many times. At the same time, you have real analysis problems. But emphasis is very slow, very low, not slow. Very, very low. Let's see here, anyway. Ordering of the real numbers. Let x and y be real numbers. We say that x is greater than y. And write x greater than y if x minus y is a positive real number. And x less than y if and only. Can you see here, that is again incorrect now. He says, and write x greater than y if. Over there if, here it is if and only if. Again not consistent. However, if is the correct thing. Did you see that?
Yes.
A negative real number. We define x greater than or equal to y if x greater than y or x equals y, and similarly define this thing. Comparing this with the definition of order on the rationals from definition 4.2.8, I cannot remember what it is, we see that the order on the reals is consistent with the order on the rationals. That is, if two rational numbers q dash are such that q is less than q dash, the rational numbers in the rational number system, then q is still less than q dash in the real number system. I think that's good anyway. And similarly for greater than, in the same way we see that definition of absolute value given here is consistent with that in definition 4.3.1. What? See, all the claims in proposition 4.2.9 which held for rationals continue to hold for real numbers. Now, I am sure you can prove them, but when you are right, make sure that you write really logical way. So then the more logical you become, the speed will be faster for you to learn. We just prove one of the claims and leave the rest to exercise. Let's see, suppose we have x less than y and z is a positive real. And we want to conclude that x is less than y is z. Since x less than y, y minus x is positive. That's the definition, no? Hence by proposition 5.4.4 we have y minus x times z is y z minus x z is positive. Product of two positive numbers is positive, you include somewhere. And hence make a positive number, make a theorem of y z is bigger than x z. As an application of this proposition, we prove let x be a positive real number, then x inverse is also positive. Also, if y is another positive real number and x greater than y, then x inverse less than y inverse. First part I guess looks easy, but second part, little thing to do. Again, the things you know. Can you see? Very often you are filling time with to prove the things you know. Then you get the problems, analysis type problems that you cannot imagine even. Emphasis is not over there. Anyway, let's go. Let x be a positive. Since xx equals 1, the real number x inverse cannot be 0. Because if x inverse 0, then x times 0 is 0. We have proved that. So x inverse cannot be 0. Also from proposition 5.4.4, it is easy to see that a positive number times a negative number is negative. Because over there, I guess he has proved positive number times negative 1 is negative. Therefore, negative, now you can extend it to that. This shows that x inverse cannot be negative. Since this would imply that xs equals 1 equals is negative. A contradiction, so x inverse then must be positive. It cannot be 0, then it is x inverse, x times x inverse will be 0. It cannot be negative, then positive number times negative number will be negative. Therefore, only choice is x inverse must be positive. Here there is a little problem. Now let y be positive as well. Now we take a number positive, right? Also if y is another number and x greater than y, then x inverse less than y inverse. Again, the result we know of. Now let y be positive as well here. So x inverse and y inverse are also positive. We have proved that. If x inverse greater than or equal to y inverse, we have to prove that x inverse less than y inverse. By proposition 5.4.7, we have that xx inverse greater than, yx inverse greater than, y inverse. Do we have it? Because the last thing we have, if x inverse greater than or equal to y inverse, you can multiply that thing by y. But the first one, when you have x greater than y, strictly greater than y, you have multiplied by x inverse, right? So then you have x inverse greater than y inverse, x is in 1, y inverse is also 1, which is a contradiction. Right? Buddha, you understand? That's we. Now, maybe I guess you are doing a mistake now. I am reading now. Because if I am going to write this thing, another 1 hour. But in your case, always you should not read like this. You take a piece of paper and write, always. That is very important. Two things matter. Your hand gets used to writing things. In Beyond, you are proving writing now. Another application is that the laws of exponentiation, proposition 4.3.12, that were previously proven for rationals are also true for reals. See section 5.6. We have already seen that the formal limit of positive rationals need not be positive. We have seen that it could be 0 as that example shows. 0.1, 0.01, 0.001, that is equivalent to 000 sequence. So the formal limit is not, when this guy says 0 here, that is 0 sequence actually, so it's kind of misleading. However, the formal limit of non-negative rationals, that is rationals that are neither positive, that are either positive or 0, is non-negative. Let's see again. However, the formal limit of non-negative rationals are non-negative. Formal limit is non-negative. Formal limit of positive rationals is not positive. We have an example on the board. But formal limit of non-negative rationals is non-negative. Let's see whether he has a proof. You understand my point? Non-negative reals are closed, he says. Let A1, A2, A3 be a co-sequence of non-negative rational numbers, then formal limit of An is a non-negative real number. There is no proof. Does he say anything? After. Eventually we will see a better explanation of this fact. The set of non-negative reals is closed, whereas the set of positive reals is open. See section 11.4. Oh my gosh, by the way. So here is proof. We are going to prove that set of non-negative reals. If you take a non-negative reals sequence, formal limit is also non-negative. That's what we are going to prove. We argue by contradiction. This is not difficult. Let's do it. And suppose that the real number x, formal limit A is a negative number. What? Keep it easy. The non-negative reals are closed. Let A1 be a co-sequence. An is non-negative. An is non-negative. Now we are going to argue. An is non-negative. We want to say formal limit also non-negative. We argue by contradiction. Suppose that the real number x is a negative real number. Then by definition of negative real number, we have x is equal to limit bn for some sequence bn, which is negatively bounded away from 0. That is the definition of a negative real number. It is a negative real number. Formal limit is sequence of negative numbers bounded away from 0. That part is very important. That is, there is a negative rational minus c less than 0 such that Bn less than or equal to minus c for all n greater than or equal to 1. On the other hand, we have n greater than or equal to 0 for all n greater than or equal to 1. He is saying there is a negative rational number. Now Bn less than or equal to Bn minus c for all n greater than or equal to 1. And An is greater than or equal to 0. for all n again greater than or equal to 1. Negative c is a negative number, no? Negative c less than 0. Now, all the bn's are here. This part. All the an's are here. Now, both of them represent the same number. This cannot happen. And if you put somewhere in between c by 2 or minus c by 2, I mean, these two sequences cannot be equivalent. That's what maybe he is saying. On the other hand, we have a greater than or equal to 0 for all and greater than or equal to 1. By hypothesis, thus the numbers a n and b n are never c by 2 close. Never. Thus the sequences a n and b n are not eventually c by 2 close. They must be equivalent. Same number. Since c by 2 greater than 0, this implies that a n and b n are not equivalent, we is saying the same thing, but this cannot respect that all these sequences have x as their formal limit. So this is very important. We have seen formal limit of sequence of positive rational numbers can be 0. However, formal limit of non-negative rational numbers is non-negative. That's what we do. Let a n and b n be co-sequences of rationals such that a n greater than or equal to b n for all n. Then formal limit of a n greater than or equal to formal limit of b n. I mean that you can prove very easily. No? Remark, note that the above property does not work because just because of a n, we discussed this in the morning also. Still I guess, no, now it is afternoon. Just because of a n greater than b n, you cannot say limit of a n greater than b n. This is not guaranteed. A n can be greater than b n, but limit, this is not sure. This is not sure. They can be equal, no? Because I wrote in the morning 1 over n is strictly greater than 1 over n plus 1, but both of them have the same limit. Greater than or equal thing is maintained, but greater than is not preserved. Now we define the distance dxy by mod x minus y, absolute value of x minus y just as we did for the rationals. Impact proportion for 3.3 and 4.3.7 hold. Not only for the rationals but for the reals, the proof is identical since the real numbers obey the laws of algebra and order that the rationals do. Where the biggest problem is to remember this, no? Which one is correct, which one is incorrect. We now observe that while positive real numbers can be arbitrarily large or small, they cannot be larger than all the positive integers or smaller in magnitude than all of the positive rationals. I mean, bounding of reals by rationals, that x be a positive real number, then there is the positive rational number q. If you take any positive real number, always you can find a smaller rational, that's what it says. And there it is a positive integer n, also bigger than x. Very important here. If you take a positive real number, you can find a smaller rational and a bigger positive integer. X lies between the positive number and integer. The thing we discussed, some similar thing, somewhat similar. Here he is proving this, I guess. Proof is not that long. So you need to keep in mind what we are going to prove. You take any x, there is a smaller rational number. See, these are real analysis things. Very important. Since X is positive real, it is the formal limit of some co-sequence A which is positively bounded away from 0. He is using his definitions. X is a positive real number. What it means is, it is a formal limit of positively, formal limit of a sequence which is positively bounded away from 0. Also by lemma 5.1.15, whatever it is, this sequence is bounded. We have learned that Cauchy sequences are bounded. We proved some time ago. Cauchy, that one is bounded. Thus we have Q greater than 0, such that Q and R bounded means whole sequences lies between two bounds. I mean, they are rational now. So far we are dealing with rational numbers. For all greater than, for all n. Because it is a Cauchy sequence, it is bounded. Bounded means there is a lower bound, there is a upper bound. So lower bound is Q, upper bound is R. They are rational numbers according to our discussion for the time being. But by proposition 4.4.1, we know that there is some integer capital N, such that R less than or equal to capital N. 4.4.1, I cannot remember exactly what it is. Since Q is positive, Q less than or equal to R, R less than or equal to N. We see that N is positive because Q is positive, because the sequence X is a positive number. So this sequence of rational number is positive and bounded away from 0. Whatever the proposition over there, 4.1, I cannot remember what it is. There is a some integer capital N greater than or equal to R. Now you have from that Q less than or equal to R less than or equal to N. However, since Q is positive, then capital N must be positive from that line. To the are you with us? We see that N is positive. Thus Q less than or equal to N less than or equal to capital N for all n greater than or equal to 1. So that is the proof. Applying corollary 5.4.10, we obtain that Q less than X. Now A for each N is in between Q and N. Then formal limit also must be in between Q and N. We have proved that before. Corollary 5.4.10. I mean, the difficulty is that you may be having hard time to remember what to forget, what is the result, what is the axiom. Maybe you have to take a piece of book like yours, axioms, results. No, otherwise it is very difficult. But after this chapter, everything, the things you want to assume will be taken for granted that they are correct. Because you cannot say axiom 5.00, who can remember? Yeah, there was a lecturer when I was a student at the University of Colombo, physics lecturer, he has died by the way. So he does not know, I don't know actually to tell the truth. The students thought he does not know the subject. So he has notes like this exam equation 49, equation 43. I don't like this because the lecturer should know the material. So in his lectures, I sleep. So I sleep. So there was a bright guy next to me. I always used to sit, both of us used to sit together. Sometimes he doesn't like when students sleep. Oh, I was about to tell his name, good to say. He's looking at you. Now look, I got up. I can hear. The condition of the node deflection is unchanged by equation 49. In I sleep. Because since he cannot say in his heart, he has to go by equations. I mean, these results, I cannot remember actually now. Over there was some proportion 4.1. I think I remembered it. The other day also we used it.
Archimedean property.
Archimedean property, that's correct. It is a very good, important one. But so I guess 10 minutes, let's go. Here, this is reasonably okay, no?
Yeah.
If you have a doubt about a proof somehow, always rewrite again. Don't do what I am doing. Because if I am going to write all of them on the board, doesn't make sense. Certain things are in the book, no? But something is not clear. If I find out that it is not clear like what I did in the board, I will prove it on the board. But now we see. Archimedean property. So this is a very important one till you die. What it says, let x and epsilon be any positive real numbers. X may be so large, epsilon may be so small. We don't know. X can be bigger than 10 billion. Epsilon can be smaller than 1 over 10 billion. What does it say? Then there is supposed to be a capital M such that m times epsilon less than x. This one says m times epsilon is you are adding epsilon m times. No matter how small number epsilon is and no matter how the number x, how big it is, regardless of that, if you add the epsilon so many times, eventually it will pass x. That's what it says. Very important. This is of course obvious, but this is the proof. Even in my book, I have proved it. It's very important. Actually, this is one reason I came to do maths. I was wondering, why on earth? How can you prove it? I mean, how can you, this is, I mean, the sun shines it, rises in the east, sets in the west. I mean, you cannot prove it, I mean, it is a fact. It is something like that, no? Anyway, see, the number x by epsilon is positive. The proof is of course obvious, and hence, by proposition 5.4.12, there is a positive integer n such that n greater than or equal to x by epsilon. Actually, that is the real Archimedean property, but he is writing like this. We said m equals n plus 1, then x by epsilon is strictly less than m. When you multiply by, you get the result. M epsilon is greater than x. I guess then he has a commentary. This property is quite important. He says that no matter how large x is and how small epsilon is, if one keeps adding epsilon to itself, one will eventually overtake x. Very important. These are naturally given any two real numbers x less than y. We can find a rational number q such that x less than q less than y. I suppose, we discussed this thing, no? See exercise 5.4.5. What does it say? 5.4.5. I cannot remember you.
Obviously.
Is that so? So I am sure you can prove it. It's not. You should prove it. This is a very, very important one if you are thinking of analysis. Between any two real numbers, there is a rational. From this, you can prove between any two real numbers, there are infinite many rationals. Not only that, using this two, you can prove between any two real numbers, there is an irrational. From that, you can prove between any two real numbers, there are infinitely many rationals. So, what we are saying is, even in between any two real numbers, there are infinitely many rationals as well as infinitely many irrationals. We use this a lot in analysis when you talk about continuous functions, differentiable functions, integrable functions. Oh, we use it almost always. Very, very important. Especially with me, I talk about examples like the function I discussed this morning, integral of every function is 2025, integral of the limit of the function is 0. It can be anything. Alright, we have now completed our construction of the real numbers. This number system contains the rationals and has almost everything that the rational number system has. The arithmetic operations and the laws of algebra and the laws of order. However, we have not yet demonstrated any advantages that the real numbers have over the rationals so far. Even after much effort, all we have done is shown that they are at least as good as the rational number system. But in the next few sections, we show that the real numbers can do more things than rationals. For example, we can take square root in a real number system. Yeah, of course. Up until now, we have not addressed the fact that real numbers can be expressed being the decimal system. For instance, the formal limit of this one is more conventionally represented as the decimal. We write like that. We will address this is in appendix this one. Did you read the appendix that one? No.
Read a bit.
It's not necessary for the time being, but we have to read something. But for now, let us just remark that there are some subtleties in the decimal system. For instance, 0.999 and 1.00 are in fact the same real number. Yeah, that gives problems. That is very important. Like to do analysis, we have to study the decimal system. That's very, very important. Prove proposition 5.4.4. In if x is not 0, what is 5.4.1? I don't know. 5.4.1.
4.4 problem. Size is 5.4.
5.4.4. Basic properties. Trigonometry. This says x is 0, x is 4, then this equation will be eventually 0, etc. Use this to show that the sequence. Eventually, either was bounded away from 0 or 0. Okay. That is. Then what is this? Do the remaining claims in proposition 5.4. And this is also a very important exercise. Show that anyway you are not going to do that soon, no? Show that for every real number x, there is exactly one integer capital N such that n less than or equal to x is less than n plus 1. This integer n is called the integer part of x and sometimes denoted by, it has a name. I cannot remember what is the name. Again, he says in proposition. Next exercise is also very important. Show that for any positive real, these are very important in analysis. Show that for any positive real number is greater than 0, there is a positive integer n such that x greater than 1 over n. Prove proposition 5.4.14. You may, I don't know what it is. Let xy be real numbers and let epsilon greater than be a positive real number. Show that mod xy less than or equal to epsilon if and only if x lies between y plus and epsilon minus epsilon. Mod x minus y less than or equal to epsilon if and only. That's a very important exercise but very easy. Let x and y be real numbers. Show that x less than or equal to y plus epsilon for all real numbers, epsilon greater than 0 if and only if x less than or equal to y. That is also a very easy but very real analysis thing. Show that x minus y less than or equal to epsilon for all real numbers, epsilon greater than 0 if and only if x equals y. That's also very easy but that is very real analysis thing. Oh, we are having to list up about property next Wednesday. let x and y be real numbers so that x less than or equal to y plus I discussed it. No? Let a and b a Cauchy sequence of rationals. Let x be a real number so that if a less than or equal to x for all n greater than or equal to 1, then formal limit is less than or equal to x. Similarly, if a greater than or equal to x for all n, then formal limit a greater than or equal to x is proved by contradiction. These exercises are not difficult, but exercise 5.4.3 is very others are, these are actually 1, 2, 3, 4, 5, 6, all of them are very important in analysis. When we are going to talk about continuous functions, differentiable functions, integrable functions, this sort of must be natural for you, but so far it is not, no? So far it is not. Again, the list of about properties of, let's not start it now. See whether you can talk well. We now give one of the most basic advantage of the real number over the rationals. One can take the least upper bound should be least upper bound. It's another name. I mean, for least upper bound is B. Actually, right, should be of any subset E of the real numbers. Upper bound, let E be a subset of R and let capital N be a real number. We say that M is an upper bound for E if and only we have x less than or equal to M for every element x in E. Did you read this? Before coming? So by reading, I am also just reading. Will it help?
Yes, sir.
Oh, M is an upper bound means every element is less than or equal to M. And that is very clear. For instance, if you take the interval x real numbers between 0 and 1, 1 is an upper bound. As a result, any number greater than 1 is an upper bound. Then 1 is an upper bound for E since every element of E is less than or equal to 1. It is also true that 2 is an upper bound for E, and indeed every real number greater than or equal to 1 is an upper bound for E. On the other hand, any number such as 0.5 is not an upper bound because 0.5 is not larger than every element of E, not element E. That's wrong. That's
For some.
for some. Did you see? Because other people will think I'm using different English words. That is incorrect. He says 0.5 is not larger than upper bound because 0.5 is not larger than every element in E. That's incorrect. Merely being larger than some elements of E is not necessarily enough to make 0.5 is an upper bound. That statement is redundant, useless. I mean, upper bound means M is an upper bound, then M must be larger than or equal to every element in the set. Then why do you say that M being merely being up there and larger than some element of E is not necessarily enough to make? It's not mathematics, no? No. Upper bound means he has written is we say that capital M is an upper bound for E if and only we have x less than or equal to M for every element x in E. That's the definition. I mean, you cannot change. 1 plus 2 is 3. Now here he says merely being, I don't know these two. Let R plus be the set of positive reals. R plus is set of all x greater than 0. Then R plus does not have any upper bound at all. Why? So let's discuss that next day. But result, intuitively we know there is no real number greater than all the real numbers. That we know intuitively, but that's not the rule. Let's discuss next day. Because when I get late, sometimes it's difficult for me to get home. There is a school very close to my home. School